Good afternoon. My name is Mark Foley from the School of Physics at the National University of Ireland, Galway. I'd like to thank the paper reviewers and the organising committee of the IEEE Sensors Conference for allowing us the opportunity to present this work. So the title of this presentation is the optimization of optimizing novel inorganic scintillation detectors for applications in medical physics. The co-authors are Kevin Byrne, Skye Conlan. We're both graduate studies who did most of the work on this. And with collaboration with Magdalena Bazalova-Carter at the Department of Physics and Astronomy at the University of Victoria in Canada. So just an overview of today's talk. We'll just introduce briefly small animal irradiations, a little bit of discussion about dosimetry, some of the previous work we've done, a little bit of background about Monte Carlo modeling and some simulations we've done in this work, and some considerations for future work. So the aim of this project was really to look at different scintillating materials and to explore, could we optimize the design of these inorganic scintillators to take advantage of their high signal output? There are clinically available plastic scintillators in the market, and they have an advantage of being water equivalent. But we wanted to explore, can we use inorganic scintillators, take advantage of this higher light output, as I said, as an alternative to plastic scintillators? So one of the applications we looked at were small animal irradiators. So one of these is called the SERP System, which you see here on the right-hand side. So it stands for Small Animal Radiation Research Platform. So this system was based at the University of Victoria, and we wanted to explore, could we use our inorganic scintillation detectors in this platform, and then could we optimize them to provide accurate and precise real-time dosimeters? So the basic concept is you're using radiation beams, and they're interacting with the scintillation materials, inorganic in our case, and the optical signal comes down an optical fiber, and we can detect the signals with photomultiplier tubes or MPPCs or some other device. And then we can actually optimize this design here of the scintillating material, change the volumes, change the scintillators, and see if we can get better performance. So as I said, we can use these ISDs for various applications, including a range of applications in medical imaging and radiotherapy dosimetry applications. So just to look at some previous studies very briefly, another medical physics application would be in radiotherapy centers. So you have options of maybe using these dosimeters in brachytherapy, and I'll speak more about that later on in the presentation, but also in LINAC dosimetry. So here on the right hand side, we see the setup in a radiotherapy center. We have a LINAC, and then we're just placing the ISD in the beam and doing some measurements, so in phantom measurements. And this was published in 2019 by one of my PhD students in the IEEE Sensors Journal. So the fiber we use in radiotherapy applications, the geometry of the scintillating tip here in the top, which is shown on the left-hand side, was a 700 micron diameter well, which was machined into the PMMA optical fiber, 7 millimeters deep. The outer diameter of this particular fiber is 2.2 millimeters. And then an MPPC made by Hamamatsu was used to collect the signals. So this was a setup used in a radiotherapy center. Slightly different to the setup we use in small animal irradiations like the SERP system we mentioned earlier. So this is a paper published this year in the IEEE Sensors Journal. And here you see the design slightly different in that we have the same diameter well, so it's a 700 micron diameter well, but we shrunk the depth to 3 millimeter depth. Then considering that we might minimize the dose perturbations created by having this dosimeter in the beam. So again, the design is quite similar, but just a smaller depth in the well. So we tested this, and we tested parameters such as repeatability, linearity, reproducibility, and then actually the packing quality within the actual well. And as mentioned, this is published this year in the Sensors Journal. We also looked at various different scintillating phosphors and benchmarked them against the bottom line here, which is your plastic organic scintillator, the BCF60. And we were testing the inorganics, the zinc sulfide doped with silver, the 3 gadox fibers, which were doped with terbium, europium, and praseodymium. And they performed quite well in comparison with the organic scintillator, which is the bottom line of the table. So this is just 3 tables extracted from our conference paper at this conference. And it's just looking at some of the designs that we've tweaked since starting this work. The first table here shows some of the designs we were using, which were mentioned just in the previous slide. So the gadox and the zinc sulfide are here, and the geometries are over here on the right-hand side. So you see we started with a 7 mil depth fiber, terbium doped gadox, and that was for radiotherapy applications where we were doing the LINAC measurements. And then we moved to the SERP system, the small animal system. We shrunk the fiber, the depth of the fiber to 3 millimeters. So you see we changed the cavity depth to 3 millimeters here. The diameter for all of them was 700 microns. And then to optimize the designs, then we moved to taking the terbium gadox fiber and shrinking the depth further to 2 mil and 1 mil, and also the diameter from 700 microns to 500 microns. And again, the logic here is to actually reduce the impact of having a high Z material. So you can see the density and the effective atomic number here. So you're talking about a density for the gadox around 7, and for the zinc sulfide around 4. So to avoid putting high density objects into the radiation beam, because there may be impacts or perturb the beam, which we'll see later to the Monte Carlo simulations. So the designs have gone from 7 mil depth to 3 mil to 2 mil to 1 mil. And our latest proposed design is a 100 micron tip. So this is the concept of dipping the actual fiber with 100 micron thickness of, in this case, zinc sulfide doped with silver on the tip of the optical fiber. And it's a 1 mil diameter. It could obviously be shrunk to 500 microns if we wanted. So we'll talk a bit about that later. Okay, so to actually explore these design optimizations, we did a lot of Monte Carlo simulations. So if we want to do that in, say, radiotherapy applications, then you need to generate a model, a linear accelerator model of the treatment head. So to build this model, you require the specifications from the manufacturer. So we signed non-disclosure agreements with Electa Oncology, and they provide us with the blueprint of their machines, and then you can build the model component by component. So you see from the target all the way down to the phantom surface. And then when you have an accurate model, this allows you then to create 3D dose distributions. And then you can actually run your simulation and include things like the dosimeter and also patient characteristics or whatever phantoms you wanted to design. So it gives you a lot of flexibility in optimizing designs. We've done the same. So the previous model you saw there was for a LINAC. This is for the small animal platform. And again, this was work that was done by collaborators in University of Victoria. They created a model which we're currently using of the SERP system. This was published in PMMA in 2018. So again, you build up your model component module by component module, and then you can include your inorganic scintillation detector in the model as well. Okay, so these models have allowed us to actually do some Monte Carlo simulations on high performance computers, and then we can explore impacts of placing these detectors in the radiation beam. So for example, these figures here, which are in the conference paper, this conference paper, you can see our dose profiles, and what we're simulating here is the proposed design, the last one I mentioned, which was 100 micron from table 3, 100 micron dipped design. So you have 100 micron depth of zinc sulfide doped with silver here. And that's a 1 millimeter diameter of scintillating material. So then we can look parallel and perpendicular to the beam, or what we call here horizontal and vertical. And we can look just before the scintillator, so just before the detector or sensor, and then just afterwards. And this allows us to look at voxels and see, does the actual fiber perturb the dose in the beam? And because this is a KV beam in animal work, any object, small object, has the potential to actually perturb the dose. And you can actually see it clearly here, that placing this detector in the beam will actually have an impact on the dose. So this impact would be reduced when you move to radiotherapy simulations or radiotherapy applications, because you're working at MV level, whereas this animal work is at KV. So this work is continuing, and they're moving from some phantom testing, but also patient testing. So applications in brachytherapy. This project received funding from the EU in the H2020 project, which started in January 2020. And this will run for 3 years. And in this project, they're actually exploring the use of these ISDs for potential applications, clinical applications in brachytherapy. So some key things we're looking at here, as I mentioned in the previous line, is the dose perturbation. So the radiation dose changes using Monte Carlo simulations, and then use that to feed back into design optimization so that you can create successful and repeatable ISD fabrication, and also validation of the ISD dosimetry characteristics using measurements both in phantoms, and ultimately we'd like to do work in vivo. So thank you very much. There's just some acknowledgements here, like the Irish Centre for High-End Computing, which provided the computational facilities for this work, and also some of our collaborators and funding agencies. Here's a list of some of the references I mentioned. Thank you very much, and I'm happy to take any questions.